The Andromeda Galaxy is approaching us at 110 kilometers per second, one of the only galaxies in the universe moving toward us rather than away, and in about 4.5 billion years it will arrive. Subscribe, there's a new one every few days. Welcome to White Space. No rush, just the cosmos. There is a point in the night sky, visible from a dark enough field, where the familiar rules seem to break down. Stars give way to something larger. The individual lights blur into a faint, elongated smear. Not a cloud, not a nebula in any local sense, but an entire system of hundreds of billions of stars so distant that their collective light arrives at our eyes as a single dim patch. You are looking at another galaxy. And the fact that you can see it at all, without a telescope, without any instrument at all, is one of the most quietly astonishing facts in the whole of human knowledge. We live inside one galaxy. We cannot step outside it. We cannot photograph it from above or map its full extent with anything like the precision we might want. And yet from our position within the disk of the Milky Way, we can look outward and see others. First the nearest, then the larger, then the most extreme structures the universe has produced. This is a journey through that expanding sequence of scale. It begins close to home, and it ends at objects so large that the word large loses most of its meaning. The Milky Way itself sits within a gravitationally bound collection of galaxies that astronomers call the Local Group. It spans roughly 10 million light-years in its longest dimension and contains over 50 confirmed members, ranging from the two dominant spirals, the Milky Way and the Andromeda Galaxy, down to tiny dwarf spheroidals containing only a few million stars, diffuse and loosely bound, hovering at the edges of detectability even with modern instruments. Most of the Local Group's members are dwarfs. The large spirals are the exceptions, not the rule. And yet it is the dwarfs, particularly those closest to us, that tell some of the most instructive stories about how galaxies interact across long periods of time. We begin not with the most spectacular, but with the most intimate, the galaxies so close to our own that they are being absorbed by it even now. While you read this sentence, the Sagittarius dwarf spheroidal galaxy holds a distinction that most people would find surprising. It is at this moment the closest galaxy to the Milky Way, and it is not arriving from elsewhere. It is already here in the sense that it has been passing through our galaxy's disk repeatedly for billions of years. Its stars are strewn in a vast stream that wraps around the Milky Way in a great arc. A river of displaced suns stretched out by tidal forces. Each time the dwarf's orbit carried it through the denser regions of our galaxy. The stream has been traced across a substantial fraction of the sky, identified through careful measurements of stellar velocities and chemical compositions. Stars in the stream share a distinctive chemical fingerprint, a particular ratio of alpha elements to iron, that marks them as originating in the same dwarf galaxy environment rather than forming in the Milky Way's disk or halo. This chemical signature is one of the primary tools astronomers use to reconstruct the history of accretion events, identifying the former inhabitants of consumed galaxies long after those galaxies have ceased to exist as distinct structural entities. What was once a coherent system of stars is now being gradually reduced to a ribbon, its identity dissolving into the larger body that has captured it. The core remnant still exists, located behind the galactic center at a distance of roughly 70,000 light-years from the Sun, but it is a shadow of what it once was. Estimates suggest that the Sagittarius dwarf has lost the majority of its original stellar mass to the tidal stripping process over multiple orbital passages. The leading arm of the tidal stream swept ahead of the core in the direction of the dwarf's motion, and the trailing arm left behind in its wake. Together contain more stars than remain in the core itself. This is a galaxy in the process of being consumed, and the consumption is nearly complete. The study of the Sagittarius stream has had an unexpected dividend. Some of the stars originally part of the Sagittarius dwarf now orbit within the Milky Way's halo and disk, mixed with stars of purely local origin. Identifying them requires spectroscopic analysis, measuring the velocities and chemical compositions of individual stars and comparing them to the known properties of Sagittarius material. The discovery that the Milky Way stellar halo contains a significant admixture of stars from accreted dwarf galaxies has reshaped understanding of how large galaxies grow. The Milky Way did not form in isolation. It assembled itself over billions of years by drawing in and absorbing smaller systems, each absorption leaving chemical and kinematic traces that persist in the halo like stratigraphic layers in a geological record. Somewhat further out, though still well within the halo of the Milky Way's gravitational reach, the Canis Major overidentity presents a similar story of assimilation. Whether it represents a distinct dwarf galaxy or a stream of stars from a partially disrupted system remains debated among astronomers. But the arc of stellar material associated with it, sometimes called the Monoceros ring, traces a structure wound around the outer disk of the Milky Way that speaks clearly of an origin elsewhere, pulled into its current shape by gravitational forces that have been operating across geological timescales. The ring has been identified through photometric surveys, appearing as an overdensity of stars at distances of roughly 7,000 to 20,000 light-years from the galactic plane in directions facing the outer disk. Its existence and the question of whether it traces a disrupted dwarf galaxy or instead represents a feature of the Milky Way's own warped and flared outer disk remains an active subject of debate in the astronomical community. The difficulty of disentangling these possibilities reflects a general challenge in near-field cosmology. The evidence for past events is preserved in the positions, velocities, and compositions of stars, but the interpretation of that evidence requires models of galactic dynamics that are themselves incomplete. These objects are not neighbors in the way we usually think of neighbors. They are not separate households separated by a street. They are more like materials in the process of being incorporated, swept up, stretched out, and eventually homogenized into the Milky Way's growing body. The Magellanic Clouds are different. They have not yet been so thoroughly captured. On a clear night in the southern hemisphere, they are plainly visible to the naked eye. Two irregular patches of light, one noticeably larger than the other, hanging in the southern sky as though they had come loose from the main river of the Milky Way and drifted a short distance away. Ancient peoples of the southern hemisphere knew them well, and they bear the name of the Portuguese explorer Ferdinand Magellan, whose crew documented them during the first circumnavigation of the Earth in the early 16th century, though the clouds themselves had been observed and recorded long before that expedition. The large Magellanic Cloud lies at a distance of approximately 160,000 light-years. Its companion, the small Magellanic Cloud, is somewhat further, at around 200,000 light-years. By cosmological standards, both are extraordinarily close members of our local group of galaxies, gravitationally bound to the Milky Way in an orbital relationship that is still being understood. For a long time, it was assumed that both clouds had been satellites of the Milky Way for billions of years, looping around it in stable orbits. More recent analysis of their velocities have complicated this picture considerably. Measurements by the Hubble Space Telescope released in 2006 and refined in subsequent years found that the proper motions of both clouds, their sideways movement across the sky as measured over time, were significantly higher than expected for objects in bound, long-period orbits around the Milky Way. The data now suggest that the Magellanic Clouds may be on their first close approach, arriving from deeper in the intergalactic medium rather than having orbited our galaxy for its entire history. If this interpretation is correct, they are not permanent satellites at all, but visitors in the process of being captured, a very different dynamical situation with very different implications for how we understand the system. Supporting this picture is the Magellanic Stream, a vast ribbon of neutral hydrogen gas that extends roughly 150 degrees across the sky, trailing behind the clouds in the direction opposite to their motion. The stream, detected in radio wavelengths through the emission of hydrogen at the 21 centimeter wavelengths, contains approximately 1 to 2 billion solar masses of gas and represents material that has been stripped from the clouds through a combination of tidal forces and ram pressure, the pressure exerted by the hot diffuse gas that fills the Milky Way's halo as the clouds move through it. The stream is connected to a leading arm, a more diffuse structure of gas swept ahead of the clouds in the direction of their motion, and to the Magellanic Bridge, a concentration of gas and young stars connecting the large and small clouds directly. The entire Magellanic System, the clouds themselves, the stream, the bridge, and the leading arm, represents a coherent structure produced by the dynamical history of the two clouds' interaction with each other and with the Milky Way. Both clouds are irregular in shape, a classification that reflects their lack of the organized spiral structure seen in galaxies like our own. The Large Magellanic Cloud contains on the order of 10 billion stars and is home to one of the most intensely studied star-forming regions in the known universe. The Tarantula Nebula, also catalogued as 30 Dorados, occupies a region of the Large Magellanic Cloud, roughly 1,000 light-years across, and is powered by one of the densest concentrations of massive stars known anywhere in the local group. At its core lies the star cluster R136, which contains a population of stars so massive, some exceeding 100 solar masses, that they emit radiation intensities that would be fatal at any distance comparable to those within our own solar system. The Tarantula Nebula is so luminous that if it occupied the same position as the Orion Nebula in our own galaxy, it would cast visible shadows on Earth at night. It is a place where stars are forming at a rate and in concentrations that have no equivalent in the Milky Way, and it has been used as a local laboratory for studying the conditions that prevailed in the young universe, when star-forming regions of comparable density were far more common. In 1987, a massive star within the Large Magellanic Cloud ended its life as a supernova, the first naked-eye supernova visible from Earth since the year 1604. The progenitor star, catalogued as Sandulik NIST 69°22, was a blue supergiant with a mass of roughly 20 solar masses. On the 23rd of February 1987, it released an energy equivalent to the Sun's total lifetime output in a burst lasting seconds. The event, designated SN 1987A, was detected first not through light but through a burst of neutrinos recorded almost simultaneously by underground detectors in Japan, the United States, and the Soviet Union. 3 separate observatories on 3 continents detecting the same brief flood of ghostly particles that passed through the Earth as easily as sunlight passes through a window pane. This neutrino detection confirmed, for the first time from direct observation, the theoretical prediction that core collapse supernovae produce a neutron star and release the vast majority of their energy in neutrinos rather than light. The light came afterward, delayed by the time it took for the shock wave to travel from the collapsed core to the surface of the star. SN A has continued to be observed for decades and has been studied in every wavelength of the electromagnetic spectrum, providing a uniquely detailed case study of how a supernova evolves over time. Today, the expanding shell of material from the explosion glows as it interacts with gas rings expelled by the star during its final stages of life, a spectacle that will continue to evolve and brighten over the coming decades. The small Magellanic Cloud is more irregular still, its structure disrupted not just by the Milky Way's tidal forces, but by its ongoing gravitational interaction with its larger companion. The cloud's body has been pulled and distorted to the point where it is not clear that it has a single center at all. Different stellar populations and gas components appear to be at different distances, suggesting that the small cloud may have been torn into a depth structure along our line of sight, rather than existing as a compact three-dimensional system. A wing of stars and gas extends from the small cloud toward the large cloud, blending into the Magellanic Bridge. The interaction between the two clouds is ongoing and has been ongoing for billions of years, with each close passage redistributing material and triggering episodes of star formation that leave their signatures in the present-day stellar populations of both systems. The relationship between our galaxy and these two irregular companions is a living, dynamic system, constantly evolving under the pull of mutual gravity. It is also, in cosmological terms, relatively young, if the first approach scenario is correct. The clouds are encountering the Milky Way's gravitational influence for the first time in their histories. What happens over the next few billion years is not fully determined. The clouds could be captured into long-period bound orbits. They could undergo a series of increasingly close passages that eventually lead to their merger with the Milky Way, or they could, under some orbital scenarios, pass through the Milky Way's influence and escape back into the intergalactic medium. The uncertainties in the current measurements of their velocities and the uncertainties in our knowledge of the Milky Way's total mass make definitive prediction impossible at present. Further from home, but still within the boundaries of the local group, sits the Triangulum galaxy, catalogued as Messier 33. It is the third largest member of the local group, after the Milky Way and the Andromeda Galaxy, though its stellar population of perhaps 40 billion stars places it well behind either of its two larger companions. Triangulum is a pure spiral galaxy, no central bar structure, no obvious distortion of its arms, and it sits at a distance of approximately 2.7 million light-years from Earth. Triangulum lacks the prominent central bulge of stars that characterizes Andromeda and the Milky Way. Its nucleus is compact and relatively dim, and its central surface brightness is low enough that the galaxy was missed by Charles Messier when he first catalogued diffuse objects in 1764. It was added to his catalogue only after being pointed out to him by Pierre Méchain. Despite its modest appearance, Triangulum is a galaxy of considerable scientific interest. Its relatively undisturbed structure, with a well-organized spiral pattern that has not been heavily disrupted by gravitational interactions, provides a useful baseline for comparison with more dynamically active systems. Its gas content is high relative to its stellar mass, making it a system where star formation is proceeding at a relatively vigorous rate. Within Triangulum, astronomers have identified a stellar nursery called NGC 604, an ionized hydrogen region so large and so luminous that it dwarfs anything comparable in the Milky Way. It spans roughly 1,500 light-years and contains hundreds of young massive stars whose radiation ionizes the surrounding gas into a glowing nebula visible across millions of light-years. If NGC 604 were situated within our own galaxy at the same distance as the Orion Nebula, it would outshine everything else in the night sky, except the Moon and the planets. What makes Triangulum particularly interesting to astronomers studying galaxy evolution is its relationship with Andromeda. The two have interacted gravitationally in the past, stellar streams connecting them have been identified, and a significant fraction of Triangulum's outer stars appear to have been drawn toward Andromeda by that galaxy's gravitational influence. Triangulum may itself be a satellite of Andromeda in a loose orbital sense, participating in the same larger dynamical system that includes Andromeda's own retinue of smaller companion galaxies. Whether Triangulum is a bound satellite of Andromeda or simply a nearby field galaxy that has experienced past interaction remains an open question, dependent on measurements of Triangulum's velocity that are at the edge of current observational precision. moving beyond the immediate neighborhood of the Milky Way, but remaining within the broader region of space that astronomers classify as the local volume. A number of distinct galaxy groups begin to come into view. The M81 group, centered on the galaxy known as Bode's Galaxy at a distance of about 12 million light-years from Earth, offers one of the most visually complex examples of gravitational interaction currently visible to our telescopes. The group contains over 36 members, most of them dwarf galaxies distributed through a volume of space roughly 5 million light-years across. Its dominant members, Bode's Galaxy, its companion Messier 82, and the large irregular NGC 2403 are engaged in a gravitational encounter of considerable consequence. Bode's Galaxy, designated M81, is a grand design spiral with two well-developed arms tracing a nearly symmetric pattern around a bright, compact central bulge. In terms of optical appearance, it is among the most beautiful spiral galaxies visible in the sky, large enough and close enough that small telescopes can resolve its overall structure, and bright enough to appear in catalogs compiled centuries before the nature of galaxies was understood. But the beauty conceals a history of disturbance. Spectroscopic observations reveal that the outer regions of Bode's Galaxy's disk have been disturbed by the same gravitational encounter that has devastated its companion Messier 82, with asymmetric features and kinematic irregularities that persist despite the galaxy's otherwise orderly appearance. Messier 82 has had its structure almost completely disrupted. Gas is being driven outward from its disk in enormous plumes, heated by the collective energy of thousands of supernovae occurring in a region of extremely intense star formation. The interaction with Bode's Galaxy is the cause. Tidal forces have funneled gas into Messier 82's central regions at rates far exceeding anything occurring in undisturbed spirals, triggering what astronomers call a starburst, a period of star formation so intense that it accelerates the galaxy's evolution dramatically compared to what would occur in isolation. The star formation rate in M82's central kiloparsec is estimated at roughly 10 solar masses per year, an order of magnitude higher than the rate in the entire Milky Way disk. The outflowing gas, accelerated by the combined pressure of radiation and stellar winds from the starburst region, and by the hot, high-pressure interiors of overlapping supernova remnants, escapes the disk in plumes extending thousands of light-years above and below the galactic plane. In hydrogen alpha photographs, these plumes appear as red filaments, glowing ionized gas caught between the forces driving it outward and the gravity trying to pull it back. A third member of the M81 group, the irregular galaxy NGC 3077, has been even more thoroughly disrupted. A substantial portion of its gas has been pulled out by tidal forces into the intergalactic medium of the group, forming a complex web of neutral hydrogen that connects all three major members. This intergalactic gas, detected in radio wavelengths, contains enough material to form millions of stars, a reservoir that the member galaxies of the group may eventually reaccrete, though the timescale for this process extends billions of years into the future. Centaurus A, located at a distance of about 13 million light-years in the southern constellation of the same name, represents a different kind of spectacle. It is one of the most extensively studied radio galaxies in the sky, a giant elliptical system distinguished by a dark dust lane cutting across its center. The visual signature of a spiral galaxy it consumed some hundreds of millions of years ago. That consumed galaxy's disk of dust and gas now lies warped and tilted across the face of the elliptical, making Centaurus A instantly recognizable in any photograph. The dust lane is not just visually striking, it is a site of ongoing star formation, as the gas from the absorbed spiral continues to condense into new stars even within the body of the elliptical that consumed it. At Centaurus A's center, a supermassive black hole with a mass estimated at around 55 million solar masses is actively accreting material, producing jets of plasma that extend outward in two directions for distances of hundreds of thousands of light years, emitting strongly in both radio and X-ray wavelengths. The inner jet, the one pointing roughly toward Earth, has been imaged in sufficient detail to reveal internal structure, knots and bright spots where the plasma encounters denser regions of material and is deflected or reconcentrated. The counterjet pointing away from us is dimmed by relativistic effects, the same physics that makes a train's whistle higher in pitch when the train approaches and lower when it recedes, applied to electromagnetic radiation rather than sound. The outer radio lobes of Centaurus A extend to distances of roughly 600,000 light-years from the nucleus, spanning a region of sky large enough that early radio astronomers mapping the sky at low frequencies in the 1940s found Centaurus A to be one of the brightest radio sources in the entire sky, despite its 13 million light-year distance from Earth. Centaurus A is close enough to study in considerable detail, and it has served as a laboratory for understanding the physics of active galactic nuclei, the energetic processes that occur when supermassive black holes feed rapidly on surrounding material. The proximity makes it possible to resolve individual star clusters within the dust lane to map the velocity field of gas near the nucleus, and to track changes in the jet structure over periods of years. It is, in some sense, a near-field version of the vastly more powerful and more distant quasars and radio galaxies that were the dominant luminous objects in the early universe, an active galaxy close enough to examine in detail, providing a window into physics that operated at cosmic scales in the universe's youth. Within the local volume, dozens of smaller galaxy groups orbit through the intergalactic medium, each one a collection of gravitationally associated systems following their own internal dynamics, while also participating in the large-scale flow of matter within the universe. The Sculptor group, the nearest galaxy group outside the local group, at a distance of roughly 10 to 13 million light-years, contains a set of spiral and irregular galaxies including NGC 253, one of the brightest and most studied spirals in the sky. The Centaurus group, somewhat further at around 13 to 16 million light-years, encompasses Centaurus A, along with a collection of fainter companions. These groups are not isolated. They are embedded in the larger scale structure of the universe, participating in flows of matter toward denser concentrations and away from emptier voids. These near galaxies represent the universe as it appears when we look at our immediate surroundings. They are all remarkable in their own ways, all embedded in gravitational relationships with their neighbors, all evolving on timescales that dwarf human civilization by factors so large as to be essentially incomprehensible in ordinary terms. But they are not especially large. Within the full range of what the universe has produced, they are ordinary. The Milky Way itself, with its diameter of roughly 100,000 light-years and its several hundred billion stars, is a mid-sized spiral. To find the truly exceptional, we need to look further, much further, and at a different category of object entirely. For most of human history, the question of how large a galaxy could be did not exist as a scientific question, because the concept of a galaxy itself did not exist in any meaningful form. The Milky Way was thought to be the entirety of the stellar universe. Faint cloudy patches in the sky were classified as nebulae, gas clouds within the Milky Way, and assigned various explanations having nothing to do with independent stellar systems. The idea that these patches might themselves be island universes, each containing billions of stars, each as large as the Milky Way or larger, was proposed and debated for decades before it was settled by observation. The settlement came in the 1920s when the American astronomer Edwin Hubble, working with the 100-inch Hooker telescope at Mount Wilson Observatory in California, identified a type of variable star called a Cepheid in what was then called the Andromeda Nebula, Sepheid variables pulsate with a period that is directly related to their intrinsic luminosity, a relationship first identified by the astronomer Henrietta Swan-Leavitt in 1908, when she systematically analyzed the brightness variations of thousands of stars in the Magellanic Clouds. Leavitt found that the Sepheids with longer periods were consistently more luminous than those with shorter periods, and that the relationship was precise enough to serve as a distance indicator. By measuring the period of a Sepheid, you could calculate its true luminosity. By comparing that to its apparent brightness as seen from Earth, you could calculate its distance. The technique required only the assumption that the period luminosity relationship was universal, that a Sepheid in Andromeda behaved the same way as a Sepheid in the Magellanic Clouds, and the distances followed from the observations. The controversy that Hubble's measurements resolved had been formally staged 4 years earlier, in April 1920, at what became known as the Great Debate, a structured scientific confrontation at the Smithsonian Institution between two prominent astronomers, Harlow Shapley of Mount Wilson and Heber Curtis of the Lick Observatory. Shapley argued for a large Milky Way that constituted the entirety of the stellar universe, with spiral nebulae as local features within it. Curtis argued for a smaller Milky Way and spiral nebulae as independent island universes at vast distances. Both men had observational evidence on their side and observational evidence that contradicted their position. The debate ended without a clear winner. Resolution came from Hubble's Cepheid measurements, which placed Andromeda definitively beyond any plausible extent of the Milky Way and established that the universe contained many galaxies. The implications were staggering, and they have continued to expand as subsequent observations have revealed a universe containing an estimated 2 trillion galaxies, distributed across the observable volume of spacetime accessible to our instruments. From Hubble's discovery onward, the contest for the title of largest known galaxy has been continuously revised upward as instruments have improved and survey coverage has expanded. The Milky Way's 100,000 light-years, impressive as it once seemed, now looks modest against the structures that systematic observation has subsequently uncovered. The galaxy NGC 6872, sometimes called the Condor Galaxy, is not the most massive known system, but demonstrates what gravitational interaction can do to galactic dimensions. Located approximately 212 million light-years away in the constellation Pavo, it has been stretched and distorted by its gravitational interaction with a smaller companion galaxy, IC 4970, which passed through or near it at some point in the relatively recent astronomical past. The result of this interaction is a pair of spiral arms extended to lengths that make NGC 6872 one of the largest known spiral galaxies, spanning a diameter estimated at around 500,000 light-years, 5 times the diameter of the Milky Way. The outermost regions of the extended arms contain very young stars, possibly formed from material swept out of the galactic disk by the tidal forces of the encounter and compressed into star-forming clouds at the tips of the arms. The gas in the most distant parts of the arms is still settling, still deciding whether it will fall back into the galaxy, be incorporated into the dwarf galaxy companion that caused the disturbance, or disperse into the surrounding intergalactic medium. NGC 6872 demonstrates something important. The boundaries of a galaxy are not fixed, and the largest galaxies are not always the most massive ones. Size and mass are related but not identical, and the most extended structures can be produced by interaction rather than by the simple accumulation of material over time. Moving to a class of objects defined by their radio emission rather than their optical appearance brings us to the radio galaxies, systems in which the dominant characteristic visible to our instruments is not the light of their stars, but the electromagnetic output of their active cores. These are galaxies containing supermassive black holes that are actively accreting material at prodigious rates, producing jets of plasma that extend far beyond the optical boundaries of the galaxy itself. The jets, when they encounter the tenuous intergalactic medium through which they travel, produce enormous lobes of radio-emitting plasma, structures that can extend for millions of light years in either direction from the galaxy's center. The radio galaxy Hercules A, also designated 3C348, illustrates the extremes of what jet-driven structures can produce. Located approximately 2.1 billion light-years from Earth in the direction of the constellation Hercules, this system hosts one of the most massive known black holes in any galaxy, with a mass estimated at around 2.5 billion solar masses, roughly 600 times the mass of the Milky Way's central black hole Sagittarius A. In optical wavelengths, Hercules A appears as a relatively unremarkable large elliptical galaxy, indistinguishable in its visual appearance from thousands of other giant ellipticals visible in deep surveys. Only when examined in radio wavelengths does its true character become apparent. The jets produced by the central black hole extend outward into two enormous lobes of radio-emitting plasma, each lobe containing rings and filamentary structures whose complexity reflects a long history of jet activity with multiple episodes of different intensity. The unusual structure of the lobes has been interpreted as evidence of successive bursts of activity from the central engine, each burst driving a new wave of plasma into the lobes and producing a new set of compression features that persist as visible rings long after the burst itself has subsided. The total linear extent of the radio structure associated with Hercules A exceeds 3 million light-years, a structure built by a black hole over a period estimated at hundreds of millions of years. The radio galaxy 3C236, located in the direction of the constellation Leo Minor at a distance of several billion light-years, held for some time the distinction of largest known radio structure, with its twin lobes extending to a total linear size of approximately 15 million light-years. This is not the physical width of the galaxy's stars, which span only a few 100,000 light-years at most, but the extent of the plasma clouds inflated by the jets over the lifetime of the system's activity. Within this larger relic structure, observations have identified a smaller, more compact radio source, evidence that the jet activity ceased for a period and was then reignited, producing a new inner source nested within the old. This nested morphology, seen in several giant radio galaxies, suggests that the engines powering these systems do not operate continuously, but cycle through periods of activity and quiescence, each new period of activity leaving its mark on the surrounding intergalactic medium. But 3C236, for all its scale, does not currently hold the record. That distinction belongs to Alcyoneus, a radio galaxy discovered in 2022 using data from the L-audio frequency array, LOFAR, a network of some 20,000 radio antennas distributed across Europe and coordinated to function as a single observatory of extraordinary sensitivity. The low frequencies accessible to LOFAR reveal radio emission from old plasma that has faded beyond detectability at higher frequencies, making it possible to trace the full extent of jet structures that more conventional radio observatories would see only in part. Alcyoneus is located approximately 3 billion light-years from Earth in the direction of the constellation Perseus. Its total extent, measured from the outermost reach of one radio lobe to the outermost reach of the other, is now estimated at more than 16 million light-years, making it the largest known structure of galactic origin yet identified in the universe. To place this in some kind of human context, 16 million light-years is a distance larger than the distance between the Milky Way and most of the galaxies in the local volume. It is roughly 6 times the separation between the Milky Way and the Andromeda Galaxy. One galaxy's jets and their associated plasma structures span a volume larger than the region of space, containing our entire galactic neighborhood. The galaxy at the center of all this emission is, by itself, not especially remarkable. Alcyoneus hosts a supermassive black hole with a mass of approximately 400 million solar masses, a substantial object but not atypically large for a galaxy of its type. The total stellar mass of the galaxy is estimated at around 240 billion solar masses, placing it in the upper range of large ellipticals but not at the extreme end. Neither the black hole mass nor the stellar mass nor the jet power, as estimated from the radioluminosity, places Alcyoneus outside the range occupied by dozens of other known radiogalaxies of much smaller physical extent. What appears to distinguish Alcyoneus is the environment in which it exists. The surrounding density of intergalactic material is unusually low, meaning that the jets have been able to travel outward for an extraordinary length of time before encountering sufficient resistance to produce the characteristic lobes. The record, in other words, may owe more to the emptiness around the galaxy than to any exceptional property of the galaxy itself. This understanding changes how we should think about records in astronomy. The largest known galaxy of a given type may simply be the one that has had the most favorable conditions for growth or propagation, the one that, by chance of cosmic location, encountered the least resistance. And it may mean that objects comparable to Alcyoneus exist elsewhere and have not yet been detected, either because they lie in directions where our surveys have not yet been completed, or because the low-frequency radio emission that reveals the extended lobes requires specific observational conditions to identify. The census of giant radiogalaxies is almost certainly incomplete. While radiogalaxies represent the current frontiers of measured galactic extent, a different category of extreme objects. The brightest cluster galaxies represents the outer limit of stellar mass and pure physical bulk. These are the dominant central members of galaxy clusters, elliptical galaxies that have grown to exceptional sizes through billions of years of merging with smaller systems. They sit at the gravitational centers of the largest gravitationally bound structures in the universe, accreting not just individual stars but entire galaxies, absorbing companions and subsuming their stellar populations into a growing ellipsoidal bulk. The galaxy IC 1101, located within the Abell 2029 cluster at a distance of approximately 1.07 billion light-years from Earth, represents one of the most extreme known examples of this class. Its diameter has been estimated at around 6 million light-years, 60 times the diameter of the Milky Way. Its mass, including the stellar component and the dark matter halo associated with the cluster, reaches into the quadrillions of solar masses. It is an elliptical galaxy composed predominantly of old red stars, the survivors of an ancient epoch of vigorous star formation that has long since concluded. The rate of new star formation within IC 1111 is far below that of younger gas-rich spirals. The galaxy sustains its growth by consuming others, incorporating the stellar populations of absorbed companions, gaining mass without generating new stars at significant rates. Each absorbed galaxy adds its stars to the growing ellipsoidal body, and those stars, having been drawn into new orbits by the gravitational potential of the merged system, gradually redistribute themselves into the smooth, slowly rotating halo characteristic of giant ellipticals. IC 1101 was first catalogued by William Herschel in 1790, who listed it as a faint nebula without understanding its nature or its extraordinary distance. It attracted little special attention until the era of systematic cluster surveys in the 20th century revealed it as the dominant central galaxy of Abell 2029, one of the more massive known galaxy clusters. The full extent of its diffuse stellar halo, the low surface brightness outer envelope that accounts for much of its enormous diameter, was only appreciated as deep imaging technology improved, making it possible to detect light from regions where the stellar density is so low that the surface brightness falls below the level of the night sky, as seen from the ground. Where IC Love-on-Love-non situated where the Milky Way currently is, its extent would engulf not just our local group, but the neighboring M81 group, the Centaurus group, and the Sculptor group as well. The Virgo cluster, which lies some 53 million light-years from Earth and dominates a substantial fraction of our local cosmic environment, is a distant neighbor by Milky Way standards. But it would fall within the boundaries of IC 1101 if that galaxy occupied our position. The scale is difficult to process. It strains the cognitive mechanisms we use to relate spatial information to lived experience, because nothing in our ordinary world provides a useful analogy. IC 1101 is also, in a certain sense, a window into the future of galaxies like the Milky Way and Andromeda. After the merger of those two spirals, several billion years from now, the resulting elliptical galaxy will begin a new phase of its evolution as a cluster center object, potentially continuing to grow through the absorption of smaller members of the local group, gradually building towards something that on a timescale of many additional billions of years might come to resemble the enormous systems we see today at the centers of massive clusters. The galaxies at the extremes of size are, in part, simply the galaxies that have had the most time in the densest environments to follow the logic of gravitational assembly to its conclusion. With these extreme objects in mind, we can return to the more intimate scale of our own cosmic neighborhood and consider in greater detail the galaxy that has attracted more human attention than any other, with the exception of our own. The Andromeda Galaxy is visible to the naked eye on any clear dark night from the northern hemisphere, appearing in the constellation that bears its name as a faint elongated smudge of light. It is the most distant object that can be seen without optical aid under good conditions, lying at a distance of approximately 2.537 million light-years from Earth. The light entering your eyes when you look at Andromeda left its source more than 2.5 million years ago, before the emergence of the genus Homo on Earth, before the first stone tools were knapped on an African riverbank, before any creature existed anywhere on our planet capable of looking up and wondering what that faint smear of light might be. Human beings have noticed Andromeda since antiquity. The medieval Islamic astronomer Abd al-Rahman al-Sufi described it in his book of fixed stars in 964 CE as a little cloud, the first written record of a galaxy beyond the Milky Way, made by a scholar who had no idea what he was looking at. European astronomers encountered it repeatedly through the following centuries, classifying it as a nebula and debating its nature. In 1764, Charles Messier included it as the 31st entry in his catalogue of diffuse objects that might be confused with comets, and it is still commonly referred to as M31 today. The question of what M31 actually was drove one of the great scientific controversies of the early 20th century and was resolved, as already described, by Hubble's Cepheid measurements in 1924. Since that resolution, Andromeda has been the subject of more sustained and systematic astronomical study than perhaps any other external galaxy. And the picture that has emerged from that study is one of extraordinary complexity and historical richness. The Andromeda Galaxy is a barred spiral, though the bar at its center is less prominent than the one in the Milky Way, and its existence was debated for some time before being confirmed through infrared observations. Its disk extends to a diameter of approximately 202,000 light-years and contains roughly 1 trillion stars. The disk is not the full extent of the system. Surrounding the disk is an immense stellar halo detected through the identification of individual halo stars using the Hubble Space Telescope and large ground-based telescopes. This halo extends to at least 500,000 light-years from the galaxy's center and may reach further. Some estimates based on the distribution of metal-poor stars and the behavior of satellite dwarf galaxies place the halo's outer boundary at over 1 million light-years. If this full extent were visible to the naked eye, Andromeda would appear roughly 6 times the angular diameter of the full moon in the night sky. The halo of Andromeda is not smooth or featureless. The Pan-Andromeda Archaeological Survey, a systematic program of wide-field imaging conducted between 2008 and 2011, mapped the outer regions of the Andromeda system in extraordinary detail, revealing a rich substructure of stellar streams, shells, and overdensities, the preserved remnants of past merging events. The most prominent of these features, the giant stellar stream, is a coherent arc of stars extending some 300,000 light-years from the galaxy's center in the direction of its southern halo. Its stars share distinctive velocities and chemical compositions that mark them as originating in a galaxy now destroyed, a dwarf elliptical that fell into Andromeda's potential, well, at some point in the past billion years, was stretched and disrupted by tidal forces, and left this arc of material as its only remaining signature. Dozens of other streams and shell features have been identified, each representing a separate accretion event, each adding its layer to the archaeological record that Andromeda's halo preserves. This record tells a story of a galaxy that has had a far more turbulent history of merging and absorption than the Milky Way. The velocity dispersions of Andromeda's stars, the statistical spread in their velocities relative to the mean rotation, are significantly higher than those of Milky Way stars at equivalent positions, indicating a more dynamically heated stellar population consistent with repeated merger events that have stirred the existing stellar distribution. Even the youngest, kinematically coldest stars in Andromeda's disk show velocity dispersions roughly 3 times higher than their counterparts in the Milky Way. Andromeda has been, in a statistical sense, more actively social than the Milky Way, more involved in gravitational encounters and absorptions, more disrupted and reorganized by these events, carrying more evidence of its past in the current state of its stars. Andromeda's spiral arms are not as cleanly organized as artists' impressions might suggest. They are fragmented, knotted in places, and interrupted by features that appear to be the scars of past interactions with smaller galaxies that have passed through or been absorbed. Infrared observations reveal multiple ring-like features in the gas distribution, including a prominent ring of star-forming gas at a radius of roughly 30,000 light-years, a feature attributed to a nearly head-on collision with a companion galaxy, possibly M32, several 100 million years ago. The collision scenario predicts that a compact galaxy punching through Andromeda's disk would send a density wave propagating outward as a ring, compressing gas and triggering star formation along its path. The ring of active star formation visible in Andromeda's disk is consistent with this prediction, and simulations of the encounter reproduce the broad features of the observed structure. Andromeda's globular clusters, dense spherical assemblages of old stars orbiting the galaxy's center, number over 450 identifiable objects and span a wider range of ages than the Milky Way's globular clusters, which are almost uniformly ancient. Andromeda contains globular clusters with ages as low as 100 million years young by stellar standards, a feature interpreted as evidence of mergers with star-forming irregular galaxies in the geologically recent past. The young clusters formed from the gas brought in by the absorbed companions, and their presence in the halo today records those past accretion events. Among Andromeda's globular clusters, one stands apart in terms of luminosity and mass. The cluster catalogued as G1, also called Mayal 2, contains approximately 300,000 stars and is the most luminous globular cluster in the entire local group. Its internal structure is unusual. It contains stellar populations of different ages and metallicities, suggesting that it may not be a true globular cluster at all, but rather the surviving nucleus of a dwarf galaxy that was captured and stripped by Andromeda's gravity long ago. At its center, observations have found evidence consistent with the presence of an intermediate mass black hole with a mass of roughly 20,000 solar masses, far larger than the stellar mass black holes produced by individual dying stars, but far smaller than the supermassive black holes found at galactic centers. The existence of intermediate mass black holes has long been predicted theoretically as a natural intermediate in the growth of black holes from stellar to supermassive scales, but confirmed examples remain rare and contested. Andromeda also harbors a class of stellar cluster that has no clear equivalent in the Milky Way. These extended clusters share the luminosity and color of ordinary globular clusters, but are several times larger in physical size, spanning hundreds of light years rather than the tens of light years typical of globular clusters. Their lower stellar density, the same number of stars spread over a larger volume, means that the stars within them are less tightly bound, more vulnerable to being stripped away by the tidal forces of the galaxy. How such clusters formed and why they appear to exist in Andromeda, but not in the Milky Way, remains unclear. They may represent a transitional class between globular clusters and dwarf spheroidal galaxies, objects that formed in the conditions peculiar to Andromeda's more active merger history, and that have survived long enough to be observed as distinct systems. At the center of Andromeda itself sits a supermassive black hole, with a mass estimated at around 100 to 140 million solar masses, significantly larger than the Milky Way's central black hole, Sagittarius A, which weighs in at about 4 million solar masses. Around Andromeda's central black hole, the Hubble Space Telescope identified something that puzzled astronomers considerably. A disk of young blue stars orbiting the black hole at close range, within a region where the black hole's tidal forces should, in principle, prevent new stars from forming. The stars are real. Their spectral characteristics confirm their youth and their high temperatures, and they orbit the black hole in a coherent disk structure, suggesting they formed in place rather than migrating from elsewhere. The leading explanation involves the possibility that star formation near a supermassive black hole can occur through the gravitational instability of a sufficiently massive and compact gas disk, where the self-gravity of the disk overcomes the disruptive tidal influence of the black hole at its center. But the details of this process remain uncertain, and Andromeda's disk of young blue stars represents one of the more intriguing unsolved problems in the study of galactic nuclei. The same central region contains a feature known as the double nucleus, two separate concentrations of light visible in Hubble images of Andromeda's core. Initial interpretations proposed a literal double nucleus, as might arise if Andromeda had recently merged with another galaxy and retained the cores of both systems. Subsequent analysis supported a different explanation. The double appearance arises from a ring or disk of older red stars orbiting the central black hole in slightly eccentric orbits, the apocenter of each star's orbit. The point furthest from the black hole, where stars move most slowly and therefore spend the most time, appears as a separate bright concentration when viewed from our perspective. The geometry of the orbit combined with our viewing angle creates the appearance of two nuclei where there is, in fact, one black hole surrounded by stars distributed in an eccentric ring. This interpretation is now broadly accepted, though the origin of the eccentric disk itself, why the orbits are eccentric rather than circular, remains an open question. Andromeda contains an enormous number of variable stars of various types. The Cepheid variables that Hubble identified in the 1920s are only the most historically significant among them. Subsequent surveys have identified tens of thousands of variable stars of many classes. Long-period variables pulsating over periods of months to years, RR Lyrae stars used as distance indicators to the galaxy's oldest stellar populations, eclipsing binary systems whose light curves encode the physical properties of the component stars. The variable star census of Andromeda is one of the most extensive of any galaxy outside the Milky Way, and it provides a multi-layered record of the galaxy's stellar demographics across all epochs of its history. X-ray observations of Andromeda, carried out primarily with the XM Newton and Chandra Space Observatories, have revealed a population of several thousand discrete X-ray sources within the galaxy. These include X-ray binary systems, pairs consisting of a compact object such as a neutron star or black hole accreting material from a normal stellar companion, as well as supernova remnants glowing in X-rays from the shock-heated gas expanding into the surrounding interstellar medium. The brightest X-ray sources in Andromeda are concentrated toward the center, where the density of older stars and the abundance of compact objects in stellar clusters is highest. Comparing this X-ray population to the equivalent population in the Milky Way provides a means of studying how X-ray source populations scale with galaxy mass, stellar age distribution, and star formation history. Andromeda has several satellite galaxies of its own, the most prominent of which are M32 and M110, visible in amateur photographs on either side of the main disk. Mestre Andrit vis a compact elliptical galaxy, a category so rare that there are only a handful of confirmed examples in the observable universe. Its unusual compactness and high stellar density suggest that it was once a larger spiral galaxy that has been substantially stripped by tidal interactions with Andromeda, leaving behind only the dense central core. The outer disk, if it existed, has been removed by repeated close passages through Andromeda's gravitational field. M110 is a diffuse dwarf elliptical, its loose stellar population partially disrupted by the same tidal forces, with evidence in its velocity field for stellar streams being pulled toward Andromeda. Beyond these prominent satellites, Andromeda is surrounded by a family of at least 24 confirmed dwarf companion galaxies distributed through its halo. A significant fraction of these satellites lie in a thin plane, roughly perpendicular to the line connecting the Milky Way and Andromeda, a configuration that has attracted considerable attention because it mirrors a similar planar arrangement of satellites around the Milky Way. Both satellite planes are unexpected within standard models of galaxy formation, which predict a roughly isotropic distribution of satellites around a host galaxy. Several explanations have been proposed, including the possibility that the satellites were accreted as part of larger filamentary structures aligned with the cosmic web, or that they represent a coherent group that fell into the local group as a unit rather than arriving individually over cosmic time. Andromeda is approaching. At approximately 110 kilometers per second, relative to the Milky Way, the galaxy is moving toward us, one of the few galaxies in the universe with a measured blue shift rather than the red shift that characterizes most galaxies as the universe expands and carries them away from us. The approach is not perfectly head-on. There is a transverse component to the motion, and measurements of that transverse component using the Hubble Space Telescope have been used to calculate the probability of different collision geometries. The broad outlines are clear. In approximately 4 to 5 billion years, the Milky Way and Andromeda will undergo their first close passage, and over the following few billion years, they will merge into a single system. The collision, when it comes, will unfold over hundreds of millions of years. It is not a collision in any visceral sense. The individual stars within each galaxy are separated by distances so vast, on average, several light years between adjacent stars in the disk, that even as the two galaxies interpenetrate, the probability of any two stars directly colliding is negligible. What happens instead is a gravitational reorganization. The orbits of stars in both systems are perturbed by the changing gravitational potential as the two galaxies pass through and around each other. Stars can be flung into new orbits, scattered into the halo, or ejected into intergalactic space entirely. The gas in both galaxies, behaving differently from the stars because it can dissipate energy through radiation, can be shocked and compressed, potentially triggering bursts of new star formation. After a first passage, the two systems will separate, decelerate, and fall back toward each other for a second encounter. After multiple passages, they will merge into a single system, a new elliptical galaxy larger than either of its precursors. Its stars moving in chaotic orbits without the organized rotation that characterizes spiral galaxies today. Computer simulations of this merger run many times with slightly different initial conditions to account for uncertainties in the current positions and velocities of the two galaxies, produce a consistent picture of the sequence of events. The first close passage produces dramatic tidal distortions in both disks, drawing out long arms of stars and gas, in the hours and days by cosmic timekeeping of the closest approach. The night sky as seen from any surviving world in either galaxy would be transformed. The compact disk of the Milky Way or Andromeda would give way to a chaotic swarm of stars from the other system, their motion perceptible over human lifetimes. Gradually, over hundreds of millions of years, the two systems would lose their separate identities, the combined mass settling into the new configuration of a merged elliptical. The gas, compressed by shocks during the interaction, would likely trigger a burst of star formation and then largely be consumed, leaving the merged system relatively gas-poor, consistent with the observed properties of large elliptical galaxies, which are thought to have formed through mergers of spirals. The Sun will almost certainly survive this process. It may be scattered from its current orbit into a very different trajectory within the merged system, possibly ejected into the outer regions of the new elliptical's halo, far from the compressed gas and dust clouds where star formation continues. What will change over these extraordinary time scales is the appearance of the night sky, gradually losing the organized band of the Milky Way as the disk dissolves, gaining and then slowly losing the dramatic visual spectacle of two merging galaxies, eventually settling into the quieter environment of a large elliptical's halo, where fewer nearby stars and a dimmer, more diffuse background replace the structured beauty of a spiral galaxy seen from within. Far from the scale of merging spirals and radio galaxy lobes, but interesting in a different way. The objects closest to our solar system tell stories about the extremes of stellar physics at the smallest scales where those physics operate. In the catalogue of known stellar systems near our Sun, few are stranger than the pair of brown dwarfs designated Luhmann 16A and Luhmann 16B, discovered in 2013 using data from the Wide Field Infrared Survey Explorer, a NASA space telescope that spent roughly 10 months scanning the entire sky in infrared wavelengths, detecting objects too cool and too dim to appear prominently in optical surveys. The discovery established that this binary system, at a distance of approximately 6.5 light-years from the Sun, is the third closest known stellar system, surpassed only by the Alpha Centauri triple system at 4.2 light-years and Barnard's star at 5.96 light-years. The existence of such a close system going undetected until the 21st century is itself a testament to the invisibility of brown dwarfs, their temperatures ranging from roughly room temperature in the coolest known examples to a few thousand degrees in the warmest, place most of their emission in the infrared, a wavelength range that was not systematically surveyed at full sky scale until relatively recently. Brown dwarfs occupy a category that exists in the gap between the most massive planets and the least massive stars. They form from the gravitational collapse of gas and dust clouds, just as stars do. But their mass is insufficient to sustain the proton-proton fusion reactions that power main sequence stars. The threshold for sustained hydrogen fusion is approximately 0.08 solar masses, or about 80 Jupiter masses. Luhmann 16A has a mass in the range of 40 to 50 Jupiter masses. Luhmann 16b is somewhat less massive. Both are, by the applicable definition, failed stars, objects whose internal temperatures and pressures never reached the levels required to ignite and sustain hydrogen burning. Brown dwarfs are not entirely inert. In their youth, when the residual heat of formation is still substantial, they burn deuterium, the heavier isotope of hydrogen, producing energy through nuclear reactions that are possible at lower temperatures and pressures than those required for ordinary hydrogen fusion. This deuterium burning phase is brief. Once the available deuterium is exhausted, the brown dwarf has no remaining nuclear fuel and begins to cool steadily, contracting as it does so. Over billions of years, it fades from the dull red glow of its youth toward the deep infrared of an increasingly cold object, eventually becoming a dark, dense sphere supported against further collapse by electron degeneracy pressure, a quantum mechanical effect that prevents the electrons within the object from being compressed into the same quantum states. The surface temperatures of brown dwarfs span a wide range depending on their age and mass. Newly formed brown dwarfs can be hot enough to glow visibly red. Old, low-mass brown dwarfs can have surface temperatures below 300 Kelvin, colder than a warm oven, colder than the surface of Venus. The coolest known brown dwarfs have surface temperatures approaching those of gas giant planets like Jupiter. At these temperatures, the chemistry of the atmosphere is entirely different from that of any true star. Water vapor condenses into clouds. Iron and silicate minerals form fine particles and layer into cloud decks. Methane accumulates in the upper atmosphere, absorbing particular wavelengths of light in ways that give the coldest brown dwarfs a spectral appearance unlike anything produced by stellar photospheres. They are, in atmospheric terms, more planets than stars, but they formed the way stars do from the top down through gravitational collapse rather than from the bottom up through accretion around a central core. The proximity of Luhmann 16 to the Sun, close enough that its parallax can be measured with straightforward precision, and close enough that its position on the sky shifts measurably over just a few months as Earth moves through its orbit, makes it an extraordinary laboratory for studying the physics of substellar objects. Using the European Southern Observatory's Very Large Telescope in Chile, astronomers were able to map variations in the brightness of Luhmann 16b as it rotated, producing the first weather map ever made of a brown dwarf. The map revealed large, bright, and dark regions on the surface, interpreted as cloud formations of different optical thickness. The rotation period of Luhmann 16b is approximately 5 hours, meaning the full surface pattern completes one rotation in a time comparable to a working day on Earth. The dominant atmospheric constituents in the spectral region probed by these observations include water and carbon monoxide absorbing and emitting at wavelengths that encode information about the temperature, structure, and composition of the atmosphere at different depths. The question of what drives the cloud patterns on Luhmann 16b is not fully resolved. On Jupiter, the most prominent cloud features the alternating light and dark bands. The great oval storms, like the Great Red Spot, are produced by a combination of rapid rotation and differential heating between the equator and the poles, which drives large-scale circulation patterns. The brown dwarf's rapid rotation might be expected to organize its cloud cover into similar bands, but the observed variations in brightness are not consistent with a simple banded structure. Instead, they appear to reflect more complex, variable cloud patterns. Large regions of thick and thin cloud cover that evolve over periods comparable to the rotation period. Whether these patterns represent long-lived storm systems analogous to Jupiter's oval spots, or whether they reflect a more transient and chaotic atmospheric circulation is a subject of active investigation. The binary pair orbit each other at a separation of roughly 3 astronomical units, approximately the distance from the Sun to the asteroid belt, with a period of about 27 years. They are gravitationally bound and will remain so for a very long time. The question of their long-term future is physically interesting. 2 brown dwarfs, each individually below the threshold for hydrogen fusion, orbiting each other at a separation of 3 ALUs, lose energy through the emission of gravitational waves at a rate so low that the orbital decay over the current age of the universe is negligible. The time scale for the pair to spiral together through gravitational wave losses is vastly longer than the current age of the universe. Any significant orbital change would require an external perturbation, a close encounter with another star passing through the neighborhood, which is a stochastic event that might occur over billions of years but cannot be predicted. If the 2 objects were somehow brought together, if some external perturbation drastically reduced their orbital separation and eventually caused them to merge, the resulting object might, depending on the total mass and the efficiency of the merger, cross the threshold for hydrogen fusion and ignite as a very low-mass red dwarf star. Red dwarf stars are by far the most common stellar type in the galaxy, constituting roughly 70 to 75% of all stars in the Milky Way, and they are also by far the longest-lived, burning their hydrogen fuel at such conservative rates that the least massive examples have lifetimes exceeding 10 trillion years. A red dwarf born from the merger of Luhmann 16A and 16B would outlive the Sun by a factor of 1,000 or more, persisting long after the Milky Way and Andromeda have merged, and their combined stellar populations have aged into collections of white dwarfs, neutron stars, and cooling brown dwarfs. There is something remarkable about the proximity of Luhmann 16 to Earth that is worth pausing on. At 6.5 light-years distance, radio signals and television broadcasts that left Earth in the years around 2020 are now arriving at that system, propagating outward through space at the speed of light, carrying encoded information about human activity on this planet. The signals continue outward at the same speed after passing the location of Luhmann 16, continuing into deeper space, eventually reaching the neighborhoods of other stars. The Voyager 1 spacecraft, the farthest human-made object, left the heliosphere, the bubble of solar wind that separates the Sun's immediate environment from the broader interstellar medium in 2012. It travels at roughly 17 kilometers per second, fast by any human standard, but absurdly slow by cosmic ones. At that speed, it would take approximately 73,000 years to reach the Alpha Centauri system, and roughly 114,000 years to reach Luhmann 16. Distance in astronomy is duration. We see all things as they were, never as they are. While considering the extremes of galactic scale, one more object demands attention. An object that confounds easy classification and has been the subject of debate since its discovery. The Sombrero Galaxy, catalogued as Messier 104, sits approximately 28 million light-years from Earth in the direction of the constellation Virgo. At that distance, it is not part of our local group or of the Virgo cluster proper, but occupies an intermediate region of space, receding from us at roughly 1,000 kilometers per second as the universe expands. It is, by any measure, one of the most visually distinctive galaxies known. In optical images, the Sombrero Galaxy appears as a bright elliptical core surrounded by a large spherical halo of older stars, bisected by a prominent dark lane of dust and gas running along the plane of its disk. The dust lane, seen nearly edge-on from Earth, gives the galaxy the appearance of the Mexican hat it is named after, a central dome rising above a flat, dark brim. This visual impression is so distinctive that M104 has appeared in more astronomical photographs and popular science publications than almost any other external galaxy. The structure of the sombrero is ambiguous in an instructive way. It does not fit neatly into any single category of galaxy morphology. Classified as an sa-spiral, a spiral with a large central bulge and tightly wound arms. It has also been described as having properties intermediate between a spiral and an elliptical, with a bulge so dominant relative to the disk that the spiral structure is almost incidental. Infrared imaging by the Spitzer Space Telescope revealed that the ring of dust encircling the galaxy's central bulge is complex in structure, containing multiple components at different radii and orientations. The infrared ring, which in optical images appears as a single dark lane, resolves into a system of nested dust structures, with characteristics inconsistent with those expected from a simple spiral disk. One interpretation that has gained some attention is the possibility that the sombrero is actually a hybrid object, a massive elliptical galaxy that has accreted a disk of gas and dust from the intergalactic medium or from a smaller companion, with that disk settling into a ring around the pre-existing elliptical's equator. In this picture, the prominent halo of old stars belongs to the original elliptical, while the dust ring represents material added more recently. A competing interpretation holds that the sombrero is a standard spiral galaxy oriented to show its disk nearly edge-on, with an unusually large and dominant bulge that makes it look more elliptical than it actually is. Distinguishing between these scenarios requires measurements of the stellar kinematics in both the bulge and the disk that are at the edge of current capabilities, given the galaxy's 28 million light-year distance. At the sombrero's center sits a supermassive black hole with a mass estimated at approximately 1 billion solar masses, one of the more massive known black holes in any nearby galaxy. Hubble Space Telescope spectroscopy revealed the black hole's presence through measurements of the velocities of stars and gas near the nucleus. These velocities, much higher than they would be if only the stellar mass were responsible for the gravitational field, indicated the presence of an enormous concentration of mass within a very small volume. The black hole's mass places it in a category shared only by the most extreme systems known, objects like the black hole in M87, the giant elliptical at the center of the Virgo cluster, whose mass of 6.5 billion solar masses made it the first black hole ever imaged directly by the Event Horizon Telescope. The sombrero's billion solar mass central black hole is currently quiescent, not actively accreting material at a high rate, but it emits anomalous quantities of X-ray radiation compared to its optical and infrared brightness, a signature consistent with some level of ongoing activity. The sombrero's halo contains one of the richest known populations of globular clusters for a galaxy of its type, over 1,200 known clusters, far more than are found around the Milky Way. The number and spatial distribution of these clusters, combined with the galaxy's distance, make M104 a valuable system for studying the formation and evolution of globular clusters and their relationship to the properties of the host galaxy. In a galaxy with so massive a central black hole and so large a globular cluster population, the interplay between the cluster system, the nuclear region, and the overall stellar mass distribution offers constraints on models of how galaxy bulges and their associated black holes co-evolve over cosmic time. The Sombrero Galaxy's dust ring contains regions of active star formation visible in ultraviolet imaging, knots of young, hot stars whose ultraviolet emission betrays their recent origin. These regions are concentrated in the inner edge of the ring, where the gas density is highest and the conditions for gravitational collapse most favorable. The coexistence of ancient metal-poor globular clusters in the halo, remnants of star formation events occurring 10 or more billion years ago, with actively forming young stars in the dust ring, reflects the multi-episode star formation history that appears to characterize so many massive galaxies. Star formation in galaxies is not a single event, but an extended process, proceeding at different rates in different regions, punctuated by mergers and interactions that redistribute gas and temporarily enhance or suppress the formation of new stars. To look at the Sombrero Galaxy is to see an object that defies the simple categories we use to organize our understanding of galactic morphology. It is neither purely spiral nor purely elliptical. Its dust ring and its stellar halo speak of different histories, possibly different origins, coexisting in a single gravitational potential. It is beautiful in its distinctiveness and instructive in its complexity, a reminder that the universe did not consult our classification schemes before producing its structures. We return finally to where we began, to the question of scale, and to the strange situation of a species capable of asking that question. The universe has assembled over 13.8 billion years, a hierarchy of structures spanning many orders of magnitude in size. Subatomic particles organized into atoms, atoms organized into gas clouds collapsed into stars, stars and gas organized themselves into galaxies, galaxies gathered into groups and clusters. Groups and clusters arranged themselves into filaments and walls surrounding enormous voids. The cosmic web, the large-scale structure of the universe, extending across billions of light years as a network of matter, concentrated along thin sheets and filaments with vast, empty expanses between them. Within this hierarchy, galaxies occupy a particularly interesting level. They are the basic unit of stellar organization in the universe, the structures within which most star formation occurs, most planetary systems form, and most of the heavy elements needed for chemistry and biology are produced and distributed. They range in mass from a few million solar masses in the smallest dwarf spheroidals to many trillions of solar masses in the dominant central galaxies of massive clusters. They range in diameter from a few thousand light years to the millions of light years spanned by the largest radio galaxy lobes, and they have been evolving continuously since the first galaxies condensed from the primordial gas less than 1 billion years after the Big Bang. We are located within one of the mid-sized examples. Our Milky Way is not the smallest and not the largest, not the oldest and not the youngest, not the most active and not the most quiescent. It is a typical barred spiral, orbited by a family of dwarf companions, approaching its nearest large neighbor at a speed that seems dramatic in human terms, but is glacially slow by cosmological standards. Within it, on a planet orbiting an unremarkable star in one of its outer spiral arms. We have spent a few centuries building instruments capable of reading the light that has crossed the universe to reach us. Instruments that have slowly revealed the extraordinary scale and variety of the structures that surround us. We have learned that the Sagittarius dwarf is being dissolved into our galaxy's halo right now, its stars distributing themselves across orbits that will carry them through the Milky Way's disk indefinitely. We have learned that the Magellanic Clouds may be visiting our galaxy's neighborhood for the first time, drawn in by gravity from the deeper intergalactic medium. We have learned that Andromeda, the galaxy that was once thought to be a mirror of our own, has a far richer and more turbulent history than the Milky Way. Its halo filled with the wreckage of absorbed companions and its disk scarred by the passage of smaller galaxies through its plane. We have learned that some galaxies have grown to dimensions of millions of light years through the energetic activity of their central black holes, building radio-emitting structures that dwarf the local group. We have learned that the most massive galaxies, sitting at the centers of enormous clusters, have been consuming their neighbors for billions of years and will continue to do so for billions more. The light arriving from these objects has traveled for millions or billions of years to reach our instruments. It carries information about conditions in the universe as they existed long before our solar system formed, long before any planet capable of supporting life had assembled its chemistry and geology into the necessary conditions, long before any eye or instrument existed to receive it. It arrives regardless, patient and indifferent, depositing information that we have only recently learned to read. The journey from here to Andromeda, if it were possible to travel, it would take 2.537 million years at the speed of light. The journey to IC 111 would take over 1 billion. The journey to Alcyoneus would take 3 billion years. The journey to the most distant objects visible in the deepest surveys would take nearly 13 billion years, back to an era when the universe was young and galaxies were just beginning to organize themselves from primordial gas. No one will make these journeys, but the light has made them, arriving here carrying information from the full range of galactic scale and structure. We read that light as best we can. We build the instruments, train the algorithms, launch the telescopes, and sit quietly in the dark, listening to what the universe has to say about how large it has grown, how varied its structures have become, and how much of it remains to be understood. The silence of a clear night sky is not emptiness. It is the accumulated signal of billions of years of cosmic evolution, compressed into the few photons that reach any given eye on any given night. Every direction leads eventually to something: a star, a galaxy, a cluster, a wall of galaxies beyond a void, and beyond that, more of the same, stretching outward to the edge of what light has had time to cross since the beginning. We are not at the center of this. We are not at the edge of this. We are somewhere within it, temporary and small and curious, doing what curious things do, asking where we are, what surrounds us, and how large it all is. The answer, so far as we know it, larger than we had imagined, and stranger. The question of what else exists, what we have not yet found, what our instruments have not yet resolved, what lies beyond the current surveys, is not idle speculation. It is the engine that drives the field forward. Every major advance in observational astronomy has revealed categories of objects that were previously unknown or unknown to be common. Radioastronomy, developed in the mid-20th century, revealed the radio galaxy phenomenon, the existence of sources of radio emission far more luminous than any stellar object, powered by processes occurring at galactic centers. X-ray astronomy, made possible by placing detectors above the absorbing atmosphere on satellites beginning in the 1960s, revealed a universe of hot gas, neutron stars and black hole accretion that had left no visible signature detectable from the ground. Infrared astronomy revealed populations of dust-obscured galaxies forming stars at prodigious rates behind dust clouds opaque to visible light. Ultraviolet and gamma-ray observations have continued to uncover new phenomena at the highest energy scales accessible to current technology. Each new wavelength window, each new generation of more sensitive instruments has added to the inventory of what exists and complicated the models used to explain it. The LOFAR survey that revealed Alcyoneus is one example of this ongoing process. The low-frequency radio sky, not well mapped before LOFAR's construction, contains a population of extended emission sources, remnant radio lobes from past periods of activity, diffuse halos of re-accelerated electrons in galaxy clusters, and the faint edges of giant radio structures like Alcyoneus that were simply invisible in previous generations of radio surveys. The census of giant radio galaxies compiled from LOFAR data suggests that these objects are more common than previously known, and that many of them extend to scales well beyond what was visible to earlier instruments. The James Webb Space Telescope, launched in December 2021, has extended the frontier of observable galaxy evolution to within the first few 100 million years of the universe's history. Galaxies found in the deepest Webb fields are, according to their measured redshifts, being seen as they existed when the universe was less than 500 million years old, less than 4% of its current age. Some of these early galaxies are more massive, more structured, and apparently more evolved than the models of galaxy formation current at the time of Webb's launch had predicted for such an early epoch. The tension between these observations and theoretical expectations has generated intense discussion and is driving revisions to models of early star formation, the timing of the first supermassive black holes, and the efficiency with which the very first galaxies assembled their stellar populations from the primordial gas. The universe, it appears, organized itself faster than we thought. Stars formed earlier, galaxies matured earlier. The large-scale structures visible in the maps of the universe, the cosmic web of filaments, walls, and voids, were already in place, at least in embryonic form, by a time when the universe was only a few % of its current age. This compressed timeline of cosmic organization has no comfortable explanation in the simplest models and is likely to require significant refinement of our understanding of the processes that operated in the early universe. The observations are real, the models must adapt. For all the knowledge accumulated over the past century of systematic observational astronomy, the inventory of what is unknown remains staggering. The nature of dark matter, the non-luminous component that constitutes roughly 27% of the total energy content of the universe and provides the gravitational scaffolding within which galaxies form, remains unknown at the particle physics level. No experiment has yet directly detected a dark matter particle. The evidence for its existence is entirely gravitational, and the most favored theoretical candidates have been searched for without success. The nature of dark energy, the component that appears to be driving the accelerating expansion of the universe and constitutes roughly 68% of the total energy content, is even more mysterious. Its existence was inferred from the observation that the expansion of the universe is speeding up rather than slowing down, an unexpected result announced in 1998 and confirmed by subsequent independent lines of evidence. What dark energy is, whether it is truly constant or whether it varies with time and space, and how it connects to fundamental physics, are open questions that no current theory adequately addresses. The galaxies we have described in this account, the dwarf companions being absorbed by the Milky Way, the irregular clouds of the Magellanic System, the spirals of the Local Group, the extreme radio galaxies at the frontiers of survey completeness, the monstrous ellipticals at cluster centers are all embedded in this framework of dark matter and dark energy. Their shapes, their clustering, their internal dynamics, and their evolution are all shaped by forces we have inferred but not directly detected, working through mechanisms we have modeled but not fully understood. The visible part of the universe, the stars and gas and dust that emit and absorb and reflect light at wavelengths accessible to our instruments, is a thin tracer of a deeper underlying structure, like the surface of a sea that reflects something of the geometry beneath it, but conceals most of the volume. To contemplate all of this from a small rocky planet orbiting an ordinary star, on the outskirts of a typical spiral galaxy, is to occupy a strange epistemic position. We are made of the same material that formed in the cores of stars and was dispersed through space by supernova explosions over the history of the galaxy. The calcium in bone, the iron in blood, the oxygen in the atmosphere, all of it processed through stellar interiors and expelled into the interstellar medium of galaxies, not unlike our own, eventually finding its way into the molecular cloud that collapsed to form the solar system 4.6 billion years ago. We are not outside the universe looking in, we are within it, composed of it, and we are looking at the rest of it from a vantage point inside one of its medium-sized constituent structures. What we see with our instruments and our eyes and our mathematics is extraordinary enough. The Andromeda Galaxy 2.537 million light-years away, visible to the naked eye as a smudge of ancient light. The Magellanic Clouds, irregular satellites of our galaxy, visible from the southern hemisphere as detached fragments of the Milky Way. The radio jets of Alcyoneus, stretching across 16 million light-years of otherwise empty intergalactic space, detected by an array of antennas distributed across a continent. The stellar halo of IC1A1, 6 million light-years around a galaxy that has grown by consuming its neighbors over billions of years. All of this exists in the same universe that contains the brown dwarfs of Lumhan 16, their surfaces mapped by infrared spectroscopy from a telescope in the Chilean desert. All of it exists in the same universe that contains our solar system, our planet, the cities and oceans and weather systems of a planet whose inhabitants have, in the last several hundred years, figured out how to read light well enough to map these structures across billions of light years. The journey described in this account covers roughly 6 orders of magnitude in distance from the nearest brown dwarf system at 6.5 light-years to Alcyoneus at 3 billion light-years. Over that range, the structures of the universe vary from binary substellar objects barely distinguishable from large planets to radioplasma lobes larger than the entire local group. The diversity of what exists and the range of scales over which the universe has assembled its structures is one of the most impressive facts about it. We will continue to look, the instruments will continue to improve, the surveys will continue to extend their reach in angular coverage, in wavelength range, in depth of sensitivity. More galaxies will be catalogued, more extreme objects discovered, more records set and broken. The universe is not finished revealing itself to us, and we are not finished building the means to receive what it has to say. For now, on this night in the sky, the light continues to arrive from 2.537 million years ago, when Andromeda last looked as it does to us now. From 1 billion years ago, when IC101 was already ancient, from 3 billion years ago, when Alcyoneus was driving its plasma jets into the intergalactic void. It arrives and we record it, and we try to understand what it means. Which is to say, we try to understand what we are part of. The answer remains incomplete. It will probably always remain incomplete. But what has been learned already, the distances, the masses, the histories, the dynamics, the extremes of scale and energy and time that the universe has produced is, by any reasonable standard, remarkable enough. Listen to the numbers. Let them settle. The nearest galaxy is being absorbed by ours right now. The most distant detectable radio structure spans 16 million light-years. The most massive nearby galaxy will collide with ours in 4 billion years. The most luminous globular cluster in the local group may be the nucleus of a galaxy that no longer exists. The weather on a brown dwarf 6.5 light-years away has been mapped from its surface brightness variations as it rotates once every 5 hours. None of this is mythology. None of it is speculation. It is the accumulated product of centuries of instrument building and observation and calculation, applied to the problem of understanding what exists beyond the immediate environment of this planet. The universe has been generous in what it has allowed us to discover. There is no guarantee it will always be so easily legible. But so far the light has been patient, and we have been persistent, and the picture that has assembled itself from these efforts is one that rewards the effort of contemplation. The sky is very large. We are very small within it, and it remains, after everything we have learned, deeply productively strange